All right, vector addition and subtraction is defined component-wise. And what that means practically for you is it's defined exactly the way that you think it should be. If I want to add or subtract two three-dimensional vectors, you just add the corresponding components. And it's exactly what you think it should be. In this case, it's going to be A1 plus or minus B1, A2 plus or minus B2 in the second component, and then A3 plus or minus B3 in the third component. And of course, a similar definition for vectors in R2. I won't bother to write that down because you understand it. What I want to focus on, since the actual arithmetic is so straightforward, there's really no surprises there, I do want to focus on the geometry of vector arithmetic because there are some surprises here. It's really nice how it can be visualized. I'm going to rewrite arithmetic. Hopefully I spelled that right. My brain is a little bit tired today and I'm a little sleepy. All right, so let me show you how you can visualize this. So let's suppose that I have two vectors, u, and I have a vector v. And I want to talk first about addition. They're going to be different pictures. So if I want to do, addition, then what I'm going to do is I'm going to take my two vectors u and v. So maybe I've got a u, and maybe over here I've got, let's not make it vertical, let's make it something like this. Over here I've got a v. And I would like to know, how do I add these vectors visually? And the idea is, if you want to add them, what you want to do is you want to float the vector v on over and put the tail of v at the head of u. And now, when you add them, the addition is this new vector going from the tail of u to the head of v. When you locate v in that way, that vector is exactly u plus v. And you might want to know, well, what if I change the order? What if I put, let's actually copy this v. What if I put v over here and I go that way? Perfectly fine. You'd put v there, and then you'd copy u, and you would put u at the head of, whoops, I can't get this to work. You'd put u at the head of your v, and you end up with the same picture. You get this parallelogram. So vector addition is really nice to see. It's this sort of diagonal across the parallelogram. So the way that I've drawn this would be, this picture is u plus v, and this one would be v plus u. I'll write it over here. This would technically be v plus u, but it's easy to see they're actually the same thing. And we'll write that down in just a moment. Subtraction is a little harder to see, but it actually is really nice as well. So if you want to talk about subtraction, then I don't want you to put the head of one vector at the other. It's different. So you want to put the vectors, think of them both in standard position. So here you've got some u, here you've got some v. Oops, let's make this one u. So here I've got u, here I've got v. And maybe I want to talk about u minus v. How do I visualize that? Well, whenever you're doing subtraction, it just goes from the head of one to the other. And here's the deal. The head of the subtraction goes to whichever one of these two is positive. So you can see here that I'm saying u minus v. And so in that case, u is positive, and so the subtraction is going to look just like that. That vector that I just drew is exactly u minus v. And so, of course, if you want to draw v minus u, you would just flip the arrow, and it makes perfect sense. So that's how you can visualize the geometry of vector arithmetic. We'll use that from time to time. It'll be important that we know, that we recognize this vector being the addition and then this vector being the subtraction. But when it comes down to actually adding and subtracting, no problem at all. You just add up the components and it's exactly what you think it should be. Okay, well let's more or less end by looking at some of the properties of vector addition. This properties hold for vectors in R2 or in R3. So addition is commutative, meaning a plus b is the same as b plus a. Of course, subtraction, it's important that you realize a minus b is just a plus this scalar negative 1b. So a minus b is saying, look, flip b, that's what negative 1b does, and then add that to a. Things are associative, right? It doesn't matter how you group the addition, it's the same. A plus the 0 vector is just A, of course. A plus minus A is just 0. And I want to point out to you, I scribbled this here in purple. Hopefully you can read it. It's the 0 vector, not the 0 scalar. So A plus minus A is 0. Make sure we get the right 0. It's the 0 vector. Constant times the sum of two vector, you can distribute across the sum. A sum of constants times a vector you can distribute. And of course, 1 times any vector is just itself. So those properties somehow all should be expected, but do make sure that you're familiar with those. All right, let's play with a couple of examples and just make sure that we're comfortable actually working out the numbers here. I think everything should be good to go, but just in case. So I've given you these two vectors, v and w, and I'd like us to compute negative v plus 2 times w. And so I'm going to begin by saying, okay, fine, negative v is going to be the vector 2, negative 3. And then I want to add 2 times w. That's going to be 2 and 10. Now I just add those up component-wise, and I get 2 plus 2 comma negative 3 plus 10. And so the vector that I get is what? 4 comma 7. So vector addition, really not a big deal when you're writing it down by hand. What about the geometry? So let's make sure we can do it. Here I've given you these two vectors. They're just floating in space. But I want you, using these two, to sketch the vector a minus 2 times b. So let's go ahead and just sketch a copy of a. Here's a. Maybe it's a little bit too long. That's fine. Let me switch my eraser. We'll just, there we go. Okay, so let's go ahead and start by sketching 2b. All right, I'll show you two different ways of doing this. So 2b, just twice as long as b, so it's going to look something like that probably. And now I know that the difference, a minus 2b, is going to go from one of these heads of the vectors to the other head, and you want to end up at the one that's positive. So a minus 2b is going to look just like that. Another way to think about it, though, is, this is 2b, by the way, is once you've sketched 2b, you could go back and say, okay, here's a, and then I'm going to sketch minus 2b, and I'm going to put it down here. There's minus 2b. And now I want to add those two. And when I add those two, then I know that I go right here. And this, again, is the vector a minus 2b. It's much faster to do it this way. But I want you to realize that you can actually flip it all around and do it that way as well. All right, very good. I think rather than have a separate video, I'll go ahead and make this one a little longer. And I want to end by telling you about the standard basis vectors. So let's start in R3. Here they are. I hat is 1, 0, 0. J hat is 0, 1, 0. K hat is 0, 0, 1. I'm going to mark these. I've got them sketched over here. So you can see I hat is the one that's in red. So let's just change its style to red. J hat is the one that's along the y-axis, one on the y-axis. So that one's the one that's purple. And then K hat is the one on the z-axis. So we said that one was blue. We do write them with a hat. You can, I guess, write I bar. I wouldn't have no problem if you do that. But for whatever reason, it's very common to put little hats over these because these are sort of special vectors. I'll mention why in just a moment. So why are they special? Let's just answer that. So it turns out if you have a vector v, and you write v in component form as sum v1, v2, v3, that's the same thing as saying v1 times I plus v2 times j plus v3 times k. Think about it for a moment and make sure that you're comfortable with that. You can see it. It works out perfectly. And so just an example of this, if I give you this vector, then you should be able to quickly realize that this is what? 3, negative 4, 2. And you might wonder, well, why do we have to use ij's and k's? It just turns out it's convenient sometimes, and you'll see it throughout the book quite a bit. So you'll need to know what they mean and be able to switch back and forth. I do want to mention in R2, there is no k, and I is just 1, 0, j is just 0, 1. These are, like I said, they're called the standard basis vectors. And that's a really important linear algebra concept. Some of you took linear algebra, and you might have remembered the basis vectors for a vector space. I won't say any more than that, but there's a lot of overlap with this in linear algebra. Okay, you've survived 10.2. Great job. In the next lecture, we're going to talk about some operations that we can perform on vectors.